we move ahead to the next module of electrons and photons. And in this module, we are going to study about the Einstein's equation for photoelectric effect. Yes, students, you heard it right. Einstein was the one who gave the equation for photoelectric effect. What actually happened was, there was a scientist called as Max Planck, which we already know. He came up with the idea that light travels in energy in the form of discrete packets, and those energy or those discrete packets he later called it as quanta of photons. He told that this energy which are in the form of packets have energy which is given by h nu, where h is universal Planck's constant and mu is the frequency of the incident light, and every packet has the same amount of energy. Later, in 1905, Einstein extended the idea of Planck and told that the light energy travels in the form of discrete packets, that is photon. He also explained the characteristics of photoelectric effect more satisfactorily with the help of the equation. How did he got that equation? He made few assumptions for that. What were the assumptions that he made? There were three assumptions that he made. These three assumptions are very important, students. Please pay attention in them. First and second assumption are very simple. He told that any incident light of radiation will have a frequency nu, and these stream of discrete photons will have energy which will be given by h nu. He also told that photons move through space with a high speed, that is the speed of light, that is 3 into 10 to the power 8 meters per second. The third assumption that he made was that when the light of frequency nu is incident on the surface, there is collision between the photons and the electrons. So to study that in detail, now let us study how we get that equation from. To study that equation, we need to consider first a photosensitive metal plate. Now any metal plate will have n number of free electrons on it. You can see all the free electrons. You can see that there is a light which is getting incident on the metal plate, and each photon will have an energy which will be given by h nu. You can see that the energy is coming and falling on the metal surface. This energy which falls on the metal surface makes sure that the photons are colliding with the electrons. After the collision with the electrons will get the energy without any kind of time lag, and electrons will definitely have a tendency to start getting excited. After getting excited, electron will liberate themselves out of the metal surface. So we know that in this case, the absorbed energy of the electron is used in two ways. The number of ways in which used are two, and the first one is the energy which is absorbed by the electron to come out of the surface. The minimum energy which is required to liberate the electron out of the surface is called as photoelectric work function, which we already have studied. The energy of light in the second way is used in the form of kinetic energy. Whatever energy which remains inside the electron, it is used in the form of kinetic energy, and electron absorbs the energy and escapes with the maximum kinetic energy. Hence, we get the final equation of energy of light or energy of incident photon as work function plus kinetic energy maximum, where we know that E is energy of photon, W naught is photoelectric work function, and Ke max is the kinetic energy maximum of the electron. So moving ahead, when we write this equation, we know that E is h nu and W naught is h nu naught. So if I take the above values and substitute in the above equation, we get the equation as h nu is equal to h nu naught plus Ke max, where Ke max will be equal to h in bracket nu minus nu naught, and I put the result in box and I mark this equation as my first equation. Students, remember, this is one of the equations that we will require while studying the numericals. So we catch hold of this equation and we move ahead. We know that the parent equation is like this, where E is equal to W naught plus Ke max, but we also know that E can be written as not only h nu, but also it is hc by lambda. And also on the similar way, W naught can also be written as hc by lambda naught. I know hc by lambda, I know hc by lambda naught, I can substitute the above in the above equation. So when I substitute it, I get something like hc by lambda is equal to hc by lambda naught plus Ke max. So Ke max comes out to be hc in bracket 1 by lambda minus 1 by lambda naught, and I mark this equation as my equation number 2. I move ahead and I write down the parent equation once again, where E is equal to W naught plus Ke max, and I know that Ke max is anytime half m V max square. So by substituting that half m V max square in the above equation, we get capital E is equal to W naught plus half m V max square, and I mark this equation as my equation number 3. I again come back to the parent equation, where we know that kinetic energy maximum can also be written as E into Vs, where E is the charge of electron and Vs is the stopping potential. When I substitute this value into the parent equation, I get the answer as E is equal to W naught plus EVs, and I mark this equation as my equation number 4. So students, with the help of this module, we studied 4 different equations of Einstein for photoelectric effect, for which he won Nobel Prize when he explained it with such beautiful examples. That is the reason why this topic is one of the most important, and it is asked in board examination for 3 marks. Thank you.